In the spring of 1935, Albert Einstein published 3 papers. One of them changed biology, one of them changed medicine. One of them, he believed, had exposed a fatal flaw in the most successful physical theory ever constructed, a flaw so serious, so foundational, so incompatible with any reasonable account of how nature operates, that the theory could not possibly be the final word on physical reality. He was wrong about the flaw, but in being wrong in the specific way he was wrong, he accidentally discovered the most consequential physical phenomenon of the 20th century, a phenomenon so radical in its implications, so destabilizing to every intuition about the separateness of things, about the independence of distant events, about the structure of space itself, that the scientific community did not fully absorb what he had found for nearly 3 decades. And when it finally did absorb it, when the mathematics was completed, when the experiments were performed, when the results were confirmed with a precision that admitted no alternative interpretation, what emerged was not a correction to Einstein's theory. It was a confirmation that the universe operates on a principle that Einstein had spent the final 20 years of his life trying to prove was impossible. The phenomenon is entanglement. And the story of what Einstein found in 1935, why he found it troubling, why science set it aside, and what Roger Penrose and the subsequent development of quantum information theory have revealed about its true significance. This story is not merely a chapter in the history of physics. It is the history of how the most fundamental feature of physical reality was discovered, misidentified, dismissed, rediscovered, confirmed, and finally recognized as the structural principle from which space, geometry, and the appearance of a classical world are derived. Entanglement is not a curious quantum phenomenon operating at the edges of physical description. It is, on the best current understanding of what the mathematics is saying, the fabric from which the universe is woven. Space is not the container in which entangled things exist. Entanglement is the process from which the appearance of space is generated. The relationship between these 2 claims, between Einstein's 1935 paper and the modern understanding of quantum gravity, is what physics has been working out, largely in silence, for 90 years. It is time to make that relationship explicit. The setup requires understanding what Einstein believed quantum mechanics was missing, and why he believed the 1935 paper demonstrated the missing element with definitive clarity. By 1935, quantum mechanics had been established for nearly a decade as the correct framework for describing atomic and subatomic phenomena. Its predictions matched experimental results with extraordinary precision. Its mathematical structure, wave functions, operators, the Born rule for calculating probabilities, was well understood. And yet Einstein remained convinced that the theory was incomplete. Not incorrect within its domain, incomplete as a description of physical reality. His conviction rested on a philosophical commitment that was, in 1935, almost universally shared among physicists, the commitment to what he called local realism. Local realism is the conjunction of 2 principles, each of which seems self-evidently correct. The first is locality, the principle that physical influences propagate through space at a finite speed, not exceeding the speed of light, so that distant events cannot instantaneously affect each other. This principle is not merely a postulate of Einstein's relativity. It is the condition for causality itself, for the coherent ordering of events into causes and effects, for the impossibility of signals traveling backward in time, for the entire structure of relativistic spacetime. Without locality, the causal order of the universe becomes undefined. Events could influence each other instantaneously across arbitrary distances, and the very concept of a sequence of causes and effects would lose its foundation. Locality is not merely a feature of Einstein's theory, it is the precondition for any coherent theory of physics. The second principle is realism, the principle that physical systems have definite properties independent of whether those properties are being measured. The moon exists when no one is looking at it. The electron has a definite position even before the position measurement is performed. Physical quantities are not created by the act of measurement. They are revealed by it. This principle seems equally self-evident. A physical theory that denies it, that asserts that physical properties are not definite until they are measured, appears to make the act of observation, the existence of observers, a fundamental ingredient in the description of physical reality. And this, to Einstein, was philosophically unacceptable. Physics should describe reality as it is, not as it appears to be when observed. A complete physical theory should assign definite values to all physical quantities independently of whether any observer is measuring them. Quantum mechanics, in its standard formulation, violates realism in precisely this way. Before measurement, a quantum system does not have definite values for all its observable properties. It has a wave function, a mathematical object that assigns probability amplitudes to all possible measurement outcomes without specifying which outcome will occur. The electron does not have a definite position before it is measured. It has a wave function spread across many possible positions, and measurement selects one of them apparently at random. Einstein regarded this as a sign of incompleteness. The quantum mechanical description, he believed, was not a description of reality, but of our knowledge of reality, a useful calculational tool that correctly predicted probabilities, but failed to describe the underlying definite reality that produced those probabilities. A complete theory, he believed, would include additional variables, hidden variables, in the terminology that became standard, that specified the definite physical properties that quantum mechanics left undetermined, and from which the quantum mechanical probabilities could be derived as statistical averages. The 1935 paper, authored by Einstein, Boris Podolsky, and Nathan Rosen, and known universally by their initials as the EPR paper, was designed to demonstrate through a thought experiment that quantum mechanics must be incomplete in exactly this sense. The argument proceeded as follows. Consider two particles that interact briefly and then separate, traveling in opposite directions to arbitrarily large distances. Quantum mechanics assigns them a joint wave function, a single mathematical object describing the combined state of both particles, not two separate wave functions for the individual particles. This joint state is what is now called an entangled state. When a measurement is performed on the first particle, say a measurement of its position, the wave function of the joint system collapses instantaneously, and the second particle's wave function collapses with it, so that a subsequent measurement of the second particle's position yields a result that is correlated with the first measurement, regardless of the distance between the particles. Einstein, Podolsky, and Rosen argued that this instantaneous correlation posed a dilemma. Either the measurement on the first particle instantaneously affected the physical state of the second particle, a violation of locality, of the principle that influences cannot propagate faster than light, or the second particle already had a definite position before the measurement was performed, and the measurement simply revealed a pre-existing fact. If locality is to be preserved, and Einstein was adamant that it must be, then the second option must be correct. The second particle had a definite position all along. Quantum mechanics simply failed to describe this definite position, assigning a wave function instead of a definite value. Therefore, quantum mechanics is incomplete. There must be hidden variables, additional physical quantities not described by the wave function that specify the definite properties that quantum mechanics leaves undetermined. The argument was logically airtight given its premises. If local realism is true, if physical systems have definite properties independent of measurement, and if those properties cannot be instantaneously affected by distant measurements, then entangled quantum systems must have pre-existing definite properties that quantum mechanics fails to describe. The EPR paper was not a claim that quantum mechanics was wrong in its predictions. It was a claim that quantum mechanics was an incomplete description of a reality that was, at the deeper level, locally realistic. Einstein was confident that the deeper level existed, and that a future, more complete theory would describe it. The scientific community's response was revealing. Niels Bohr published a rebuttal within months, arguing that the EPR argument rested on an illegitimate application of classical concepts to quantum systems, that the question of what properties a quantum system has independent of measurement was not a meaningful physical question, that quantum mechanics was complete in the only sense that completion could mean for a physical theory, and that Einstein's insistence on local realism was a philosophical prejudice rather than a physical requirement. The debate between Einstein and Bohr, the most consequential scientific debate of the 20th century, ended not with resolution but with exhaustion. Einstein remained unconvinced. Bohr remained unconvinced, and the physics community, faced with a philosophical dispute between two giants that seemed to have no experimental resolution, largely set the question aside and continued using quantum mechanics to make predictions, declining to worry about what it meant. This is the silence. Nearly 3 decades during which the most fundamental question raised by the EPR paper, is local realism true, and if not, what replaces it, was not seriously pursued, not because the question was unimportant, because it seemed unanswerable. The EPR argument was a thought experiment about the interpretation of the formalism, It generated correlations between distant measurements, but those correlations could always be explained within quantum mechanics as consequences of the joint preparation of the particles, without invoking any mechanism by which the measurement on one particle affected the other. The quantum mechanical predictions were consistent with local realism as long as one was willing to postulate hidden variables, and a theory with hidden variables, a theory in which particles have definite properties all along which quantum mechanics simply fails to describe, was in principle possible. It was not ruled out. It was simply unattractive to most physicists who found the Copenhagen interpretation more parsimonious and more natural. The question remained open, and open questions, when they seem intractable, tend to be ignored. What ended the silence was not a new experiment, it was a new theorem. In 1964, the physicist John Bell published a mathematical result of extraordinary consequence. Bell showed that the predictions of any local hidden variable theory, any theory in which particles have definite pre-existing properties, and in which measurements cannot instantaneously affect each other across arbitrary distances, are constrained by a set of mathematical inequalities. These inequalities, now called Bell inequalities, specify the maximum correlations between measurements on distant entangled particles that any locally realistic theory can produce. Quantum mechanics. Bell showed predicts correlations that violate these inequalities, correlations stronger than any local hidden variable theory can generate. The question of local realism versus quantum mechanics was no longer a philosophical dispute about interpretation. It was an empirical question. Measure the correlations between entangled particles. Check whether they satisfy the Bell inequalities. If they do, local realism survives. If they do not, local realism is false. The experiments were performed first tentatively in the 1970s with results that pointed toward violation but were subject to various technical objections, then more carefully, more precisely, with progressively more sophisticated experimental designs that closed the loopholes one by one. The definitive experiments performed in the 1980s by Alain Aspect and his collaborators, and subsequently confirmed with increasing precision by dozens of experimental groups, found unambiguous violation of the Bell inequalities in precise agreement with the predictions of quantum mechanics. Local realism is false. The universe does not operate according to the principle that distant systems have definite pre-existing properties that measurements merely reveal, and that measurements on one system cannot instantaneously correlate with measurements on another. The correlations are real. They exceed what local realism permits, and no locally realistic theory can reproduce them. What Einstein found in 1935 was not a flaw in quantum mechanics. It was the most fundamental feature of quantum mechanics, the feature that distinguishes it most deeply from any classical description of reality, the feature that has no analog in any prior physical theory, the feature whose full implications physics has been working out ever since. He found entanglement. He found the phenomenon of two particles sharing a joint quantum state that cannot be decomposed into separate states for the individual particles, a phenomenon in which the correlation between distant measurements exceeds any locally realistic bound, in which the results of measurements on one particle are instantaneously correlated with measurements on the other, regardless of the distance between them, in which the separateness of distant things that we take as the most basic feature of spatial reality turns out to be, at the quantum level, an approximation rather than a fundamental truth. But there is a problem with stopping the account here, because the experimental confirmation that local realism is false, while it establishes that entanglement is real, and that its correlations exceed any locally realistic bound, does not by itself tell us what entanglement is. It tells us what it is not. It is not a consequence of pre-existing properties. It is not explicable by any locally realistic mechanism. But the positive account, the account of what entanglement actually is, what it reveals about the structure of physical reality, why the universe operates this way rather than any other, this account requires going beyond the Bell theorem and the experimental confirmations. It requires taking seriously the implication that Penrose, among others, has pursued with the greatest rigor, that entanglement is not a curious feature of quantum systems added on top of an independently existing spatial structure. It is the process from which spatial structure is derived. Here is section 2. The claim that space is derived from entanglement rather than entanglement occurring within space requires a precise formulation, because it inverts an assumption so deeply embedded in physical thinking that it rarely presents itself as an assumption at all. Space, in the ordinary understanding, is the container, the arena within which physical systems exist, within which particles are located, within which fields propagate, within which entangled particles separate and travel to their respective detectors. Space is what entangled things are separated by. It is what makes them distant. It is the reason their instantaneous correlation is surprising, because they are far apart in space, and yet their measurement outcomes are correlated as if the distance between them were irrelevant. Space on this picture is prior to entanglement. It is the background within which entanglement occurs. The reversal of this picture emerges from the conjunction of two developments in theoretical physics that occurred independently but converged over the course of the 1990s and 2000s into a single framework of extraordinary explanatory power. The first development is the holographic principle and the ADS-CFT correspondence, which established that the geometry of a spatial volume is encoded in a quantum field theory defined on the boundary of that volume, that the bulk geometry, including the spatial relationships between points in the interior, is derived from the quantum description on the surface. The second development is the realization, emerging from the detailed mathematical analysis of ADS-CFT, that the specific feature of the boundary quantum theory responsible for generating spatial geometry in the bulk is entanglement. The entanglement structure of the boundary theory, the pattern of quantum correlations between different regions of the boundary, determines the geometric structure of the interior. Change the entanglement, and the geometry changes with it. Remove the entanglement, and the geometry dissolves. Space in the bulk is woven from the entanglement of the boundary. This is not a metaphor. It is a precise mathematical statement, derivable from the formalism of ADS-CFT and supported by a body of calculations that has grown substantially over the past 2 decades. The Ryu-Takayanagi formula, one of the central results of this program, establishes a quantitative relationship between the entanglement entropy of a region of the boundary theory and the area of a minimal surface in the bulk geometry. Entanglement entropy is a measure of how strongly a region is entangled with its complement, how much quantum information is shared between the two parts of the boundary. The area of the minimal surface in the bulk is a geometric quantity, a feature of the spatial structure of the interior. The Ryu-Takayanagi formula equates these two quantities, establishing a direct mathematical relationship between a quantum informational quantity on the boundary and a geometric quantity in the bulk. Entanglement generates geometry. The pattern of quantum correlations on the surface determines the shape of the space within. What this means for entanglement between distant particles, for the EPR correlations that Einstein found so troubling, is that the distance between the particles is not a fixed background feature of an independently existing space. It is a derived quantity determined by the entanglement structure of the quantum state that describes the system. Two particles that are highly entangled with each other correspond in the bulk geometric description to particles that are close together, connected by a short geometric path through the interior. Two particles that are weakly entangled correspond to particles that are far apart, separated by a long geometric path, and two particles that are completely unentangled, whose quantum states are entirely independent, correspond to particles that are in completely disconnected regions of the bulk, with no geometric path between them at all. Spatial distance is a measure of entanglement. Spatial separation is a consequence of the degree to which quantum systems share information. Space is the geometric expression of the entanglement structure of the quantum state of the universe. This transforms the EPR paradox from a puzzle about how distant particles can be correlated into a statement about the geometric structure that entanglement generates. The two particles in the EPR experiment are not distant things that happen to be correlated despite their separation. They are things whose apparent separation is itself a consequence of the quantum state, a geometric feature derived from the entanglement structure that also produces the correlation. The correlation is not surprising given the separation. The separation and the correlation are both consequences of the same quantum state. The entanglement determines both the geometry and the correlation simultaneously. There is no independent spatial arena in which entangled particles are located and across which their correlations mysteriously propagate. There is only the quantum state, from which both the spatial relationships and the measurement correlations are derived. Einstein was troubled by entanglement because he believed space was fundamental, and entanglement was a phenomenon occurring within it. The correct relationship is the opposite. Entanglement is fundamental. Space is what entanglement produces. Einstein's discomfort was the discomfort of someone who had correctly identified that entanglement was inconsistent with his picture of space as a fixed, locally realistic background, but who drew the conclusion that entanglement must be wrong rather than that space must be derived. He was right that entanglement and local realism cannot both be true. The experimental evidence establishes this beyond reasonable doubt. What he could not accept was the alternative, that space itself, the arena of local realism, is not fundamental. That locality, the principle he regarded as the precondition for any coherent physical theory, is an emergent property of a more fundamental quantum description in which locality does not appear as a primitive concept at all. Locality on the entanglement first picture is an approximate feature of the classical geometric description that emerges from the quantum state when entanglement is structured in specific ways. In the classical limit, when the quantum state of a large system is such that different regions are entangled in the specific pattern that generates a smooth classical geometry, locality hold to excellent approximation. Physical influences propagate through the generated space at speeds limited by the causal structure of the geometry. Events that are spatially separated are causally independent. The local realistic picture that Einstein insisted upon is an accurate description of the classical world. But it is accurate because the classical world is the regime in which the entanglement structure of the quantum state happens to generate a smooth local geometry. It is not accurate because locality is fundamental. It is accurate because the quantum state that generates our classical world is one whose entanglement structure produces local behavior as an emergent consequence. This is why the Bell inequality violations do not produce observable faster-than-light signaling, despite the instantaneous correlations between distant measurements. The correlations are real, they exceed any locally realistic bound, but they cannot be used to send information faster than light, because the outcomes of individual measurements are random, determined by the quantum state, but not controllable by any local operation on either particle. The ability to exploit the correlations for signaling would require coordination between the two measurement sites that itself requires a classical communication channel, which is subject to the speed of light constraint. The entanglement operates below the level of classical locality at the quantum level from which classical locality is derived, and its effects at that level do not violate the emergent classical constraint, even though they exceed what any locally realistic mechanism at the classical level can produce. The consistency of entanglement with special relativity is not a coincidence. It is a consequence of the fact that relativity describes the causal structure of the emergent classical geometry, and the entanglement that generates that geometry is not subject to the constraints that the geometry imposes on processes occurring within it. Now consider what Roger Penrose contributes to this picture, and why his contribution is essential to understanding not merely what entanglement is, but what it implies for consciousness, experience, and the nature of the physical process that generates classical reality from quantum possibility. Penrose's central insight, developed across decades of work on the mathematical foundations of quantum gravity, is that the process of quantum state reduction, the collapse of the wave function, the selection of a definite outcome from a quantum superposition, is not merely a feature of the quantum mechanical formalism that requires interpretation. It is a real physical process grounded in the geometry of space-time, occurring at the Planck scale, and constituting the fundamental mechanism by which definite classical facts are generated from quantum possibilities. And entanglement, on Penrose's account, is directly implicated in this process. When two systems become entangled, their quantum states are no longer separable. They cannot be described independently. The joint state is a superposition of correlated possibilities, and the reduction of this superposition to a definite outcome is a single event that affects both systems simultaneously, regardless of their spatial separation. On the standard account, this simultaneity is puzzling because it appears to violate locality. On the entanglement first account, it is not puzzling at all. The spatial separation between the systems is a feature of the classical geometry derived from their quantum state. At the quantum level, the level at which the reduction event occurs, there is no spatial separation. There is only the joint quantum state, and its reduction is a single geometric event in the space-time structure, not two spatially separated events that must somehow be coordinated across a distance. Penrose's objective reduction hypothesis locates this event in the quantum geometry of space-time at the Planck scale. The reduction occurs when the gravitational difference between the superposed configurations reaches a threshold, when the quantum uncertainty in the spacetime geometry generated by the superposition constitutes one Planck unit of gravitational energy. At this threshold, the superposition resolves, a definite geometric configuration is selected, a classical fact is produced, and because the entanglement structure of the quantum state determines the spatial geometry of the classical description, the reduction event simultaneously determines both the definite outcome of the measurement and the spatial relationship between the systems in the classical geometry that the reduction produces. The measurement outcome and the geometry are not two separate things that the reduction event determines independently. They are two aspects of the same geometric event, the selection of a definite classical spacetime from among the superposed quantum possibilities. This is where the 1935 EPR paper connects with full precision to the contemporary understanding of quantum gravity and the holographic principle. Einstein found a phenomenon, entanglement, that he believed was incompatible with the correct picture of physical reality. He was right that it was incompatible with local realism. He was wrong to conclude that this incompatibility was a defect in quantum mechanics. The defect was in the picture of reality, in the assumption that space was the fundamental container within which quantum systems existed and interacted. The correct picture, assembled from the holographic principle, the Ryu-Takayanagi formula, the objective reduction hypothesis, and the experimental confirmation of Bell inequality violations, is that entanglement is the fundamental process from which space, geometry, locality, and classical reality are derived. The EPR paper did not expose a flaw in quantum mechanics.